Okay, our lecture today comes from section 8.4, Radical Notation for Nth Roots. You can see we have several learning goals. Some of them have been carried over as we proceed through the chapter, but we want to be able to evaluate radicals. We want to rewrite or simplify expressions with radicals, apply the properties that we've been using for radicals and nth root functions, and then solve real-world problems that model equations that have these radicals in. So let's get started right away and talk about our radical notation. Now, if you remember, we had been talking about radical notation versus rational notation. So as a quick reminder, this n root x was radical notation. So in this section, we want most of our work to be in radical form. And then this method was rational. And now that was chapter 7 work. So the two should go hand in hand. We should be getting used to them. So if we say radical again, and it's a power underneath a root, like this one, then we should be able to say that's the same as taking the root first, then the power, or if you want, back to the rational look of x to the power of mn. So something we talked about previously, that order really doesn't matter. It does make a difference if you're doing it in your head only, no calculator. And the last one, if you have a product of a root, which is what this represents, you can break it down into each part, the x value times the y value underneath the square root. So we're going to use those properties to help us reduce, simplify things when necessary. In order to do that, let's take a look, and maybe let's look at just the number ones first. So here we go. Everything that has just a number in, and take a good look at the different roots we have. So our thinking's been good. We've done this before. We want to continue to do that. So if we say, on the first one, what is that one number that multiplies by itself 3 times to give me 27? You should be able to say that. You should be able to know that without having to do any work on a calculator, etc. So if you are more comfortable, because we just finished the chapter, and saying, well, that's the same as 27 to the 1/3 power. They both mean the same thing. We're working in radicals, so let's try to keep this chapter in radical form. So what is that one number that multiplies by itself 3 times to give you 27? Most of you said, hey, that's 3. Then we scoot over. Next one. What is that one number that multiplies by itself 6 times to give me the number 64? In this case, it can't be very big, so if we start with the 2, say 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 more, which is our 6th factor, is 64. Then we'd say the square root, or sorry, the 6th root of 64 is 2. Then, if we start getting bigger, 2,401, and we're looking for a 4th root, and if you don't know it, you're not going to do that one in your head. Remember, you could always enter it on your calculator as to the 1/4 power, or even better yet, you could say to the 0.25, and you probably wouldn't even need the parentheses then. So 2,401, what number multiplies by itself? If you were having to do it by yourself, it's only 4 things, and you're saying, well, a minute ago, 2 is definitely too small. 3 is definitely, okay, so you might go to 5. But when you multiply by 5s, you can't end in a 1 or 0. So then we go to 6 next. Well, 6 times 6 is 36, and if we did 2 more 6s, that's a 6, a 36 times 36, which is a 6 times 6 in the first digit. When we multiply those two, it would not give us a 1. So the next number we choose is a 7. 7 times 7 is 49. That would be 2 49s, and a 9 times 9 is 81. Now we have a chance. That's the thinking you need to do. Don't just try numbers. And so, as we already said, or maybe we didn't, that the 7th root of 2,401, I said 7th root, 4th root of 2,401 is 7. Okay, so these wouldn't even been a possibility. that one did. You can multiply it out by hand or with your calculator. Now, the only difference here, and here's where the thinking gets a little different. Now, when we introduce variables in as well, you got to keep in mind what root you have. And to come out of a square root, you need groups of 2. To come out of a cube root, groups of 3. Come out of a fourth root, groups of 4. So let's try that on this first one here. You have x and y, so you can't multiply those together. So, question is, how many groups of 4 are in x to the 4th? Most people will say 1. Good. That means x to the 4th comes out as x. Y to the 8th. How many groups of 4 are in y to the 8th? 2. If you have no leftovers, then we have a perfect combination. And it happens to be a perfect fourth root combination. Go to the next one. What happens when we do have leftovers? So I didn't change anything except for the exponent underneath. So this time, I'm going to say, what is the biggest power of 4, and then any leftovers? So when I think of that x to the 5th, I'm thinking of x to the 4th times x to the 1st. One whole group of 4 with one leftover. And then with the y, obviously we're not going to change our thinking. Y to the 8th is still 2 groups of 4. So to simplify this one, we again would have an x out front. We would have a y squared out front. But we would still have a fourth root with a value of x remaining. Because without that value of x, there's no way we can get back to what we started with, which was x to the 5th. All right, our next one. Think of it in two parts. Think of the number part, and then separately, think of the variable part. You want to do fourth roots of both those numbers. So what is that one number that multiplies by itself 4 times to give you 32? Some people jump out and say, 2 does. Well, be careful. 2 times 2 is 4, times 2 is 8, times 2 is 16. So I think it's a 16. So we're going to break this 32 down into 16 times 2. We're sort of going to break the x to the 10th down also. Groups of 4. That means we have a group of 8 that is a multiple of 4, but then we would still have 2 more left over. So if we have a fourth root, still, some of these numbers are perfect fourth roots, some of them are not. Let's underline the ones that are perfect and should be coming out when we do our simplifying. Everything else should stay underneath. So here we go. The fourth root of 16, 2. The fourth root of x to the 8th means how many groups of 2 or groups of 4 are there? And there's 2. So x to the 2nd. And then we have a fourth root of the numbers that remain. We have a 2, x squared. Make sure that little 4 is there, because without it, move it up so you can see them. Without it, you would have an incorrect answer. All right, moving on. Now if we say rewrite it and assume all your variables are positive, which means we don't want to worry about is x a positive or negative number. Can I take it out with a negative number? Can I take it out with a positive? We're going to assume everything is positive, so yes, we can take it out. Now in this case, again, we want to work with the roots, and I got a different one on each one, so your brain has to be thinking. So I'm just going to subdivide right now, and we've got that. So we've got 4 different combinations here. They get a little more involved each time. All right, so let's go. Rewrite them. Rewrite them means simplify as well. Yeah, you could rewrite them and go x to the 8th power and 4th root, but you could also say, how many groups of 4 is x to the 8th? And most people will say, that's x squared. 2 groups. And it's a perfect combination. Nothing stays underneath. Next one, how many groups of 3 are in y to the 18th? How many perfect groups of 3? Well, there's 6 exactly. And so we'd end up with y to the 6th. Next one, we start throwing in some numbers as well. We're back to square roots. So square root of 4 is a perfect square. X to the 4th is a perfect square. Y to the 5th is not. So you want to rethink of that, rewrite it as the biggest group of 4 and its leftover. So now here we go. What comes out as a perfect square? Well, the 4 comes out as 2. X to the 4th comes out as x squared. y to the fourth comes out as y squared, and that still leaves us the square root of 1y left underneath to be discussed, hopefully to be paired with something else later. Then our last one is our fifth root. So again, ask yourself, is 32 a perfect fifth root number? If you don't know, you start saying, what multiplies by itself 5 times to get me to 32? 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 32 is a perfect fifth root. X to the 10th is a perfect combination of 5s, and y to the second is not. So let's bring out what we can. Fifth root of 32, 2. Groups of 5 in x to the 10th would also be 2, but write it as x to the second. And that leaves us a fifth root of y squared underneath, still to be used later. Cannot come out. It's not a perfect root. So we should be able to see how these are working, powers, roots, etc. Now this is a little different look. Take a look. I have a square root originally around the x, and then I have a sixth root. And it says rewrite using rational exponents. So you want to say, oh, rational exponents, those are those fraction looks. So you're thinking x to the power of m over n. So let's break this down. We have an x on the very inside, and it is a square root. Well, as an exponent, a square root is nothing more than 1/2. Let's put parentheses around that. And then around that, we have a sixth root. And a sixth root is nothing more than 1/6. So there's the problem. Simplify it as far as we can. We should know that's nothing more than x to the 1/12. Again, this look that we had with several radicals is called nested. One just sits nicely right over the next, right over the next. And so nested radicals. All right, we should be good with that nested stuff. And if you have any questions about the radicals or how to write them, or radical is confusing compared to rational, or rational is the one that's still hard, please bring those kind of questions with you to class.